Hello and welcome to the sixth video in our lecture on remote user authentication. In our previous video, we had a failed attempt at implementing mutual authentication. So in this video, we're going to do a second attempt. And for that, we're going to remember that even though we had a failed attempt in a previous video, what we did also in the previous video, we did have a successful attempt at one-way authentication, not mutual, but one um, process was able to authenticate itself to the other. So I'm going to go back to the protocol we had a couple slides back, where again, the two parties were called, say, Alice and Bob. And in this particular scenario, Alice was authenticating herself to Bob. And the way this protocol would work, Alice would send a message or an identifier to Bob saying, here is my username, or here is my identity. And then Bob would send Alice a challenge or nonce or random number R. And then finally, Alice would send back an encrypted version of that nonce using symmetric encryption. So she would use a shared key that both parties knew to authenticate herself. So this was a successful attempt, if you remember, at Alice authenticating herself to Bob. And so our second attempt at mutual authentication will be as follows. We're going to say, well, if Alice can authenticate herself to Bob, why can't we duplicate this mechanism and then implement it a second time, but by swapping the roles of A and B? So maybe B could authenticate himself to Alice using a symmetric set of messages. And what did not work in the previous attempt was that there was a single nonce that was used for both directions. So here we're going to use two different nonces. So RA, which is chosen by Alice, and then RB, which is chosen by Bob. So this is what this protocol that we're now proposing is. It's just the result of applying this protocol twice in both directions. So here is how the protocol would work. Alice is going to send both her identifier and a challenge to Bob, a random number R sub A. Bob is going to be able to authenticate himself to Alice by responding with the response that is the encryption of that challenge using their shared symmetric key. And at the same time, Bob is going to send a challenge, a different challenge, to Alice, and she's going to use that challenge to authenticate herself to Bob by sending back the encrypted version of Bob's challenge as her response. So the first thing I want to mention to you is that you can see, I want you to see that this, even though it looks like it's only taking 3 messages, just like this one, it is actually implementing twice or 2 copies of this protocol. We just optimized the number of messages by compressing them. So let me show you how I did that. You realize that if we did this protocol twice, we would have 6 messages. So how did we go from 6 to 3? Well, the first thing we did is we saved 2 messages by concatenating the identifier from Alice and her challenge to Bob in one message. So this is 1 message instead of 2. Similarly, we concatenated the response from Bob with his challenge. So here we saved 1 message using this concatenation. And so we went from 6 to 4. Now, how were we able to save 1 more message? Well, notice one thing that's missing here is that there is no identifier sent from Bob to Alice. So we saved this step when this protocol was played backwards from Bob to Alice. So why is that? Well, in this case, Bob does not need to send an identifier to Alice. So this is how we saved the third message to go from 6 down to 3, because Alice is the one who initiated the communication protocol. And so she sent a message to Bob. So she already knew the identity of the receiver. She picked him and sent her the message. So you might say, well, okay, but how did she know it was Bob? Well, she thought it was Bob. And the reason she ended up knowing it was Bob is because he was able to send her a response back to her challenge. So notice Bob was able to authenticate himself without having to send his identifier, because presumably Alice already knew who he was when she sent him the initial message. In any case, this is just an efficiency concern. It's not the most important, but we were able to implement this 3-message protocol twice, from A to B and from B to A, using only 3 messages, and we should always try to minimize the number of messages in any protocol. So now I want you to pause the video and to convince yourself that indeed this succeeds as mutual authentication, and that also it prevents replay attacks because of the use of 2 nonces. Okay, well, this is actually not the case. So I hope you really tried hard to break this protocol, because this is going to be a skill that is very useful and for you to develop throughout that class, is to always try to break any protocol that I give you. This is going to be something that's very informative, and you will realize doing so that it is very, very hard to design and implement a secure protocol. So actually, this protocol does not work. So again, if you didn't find a way to break it, please stop the video again and try really hard a second time. And the hint is that we're going to find a way for Trudy to actually impersonate Alice without Bob noticing. So why don't you go ahead and try to break this proposed version of the mutual authentication protocol. Okay, so let's assume that Trudy is impersonating Alice. So the first message in the protocol is Trudy pretending to be Alice, sending a random number of her own choice as a challenge to Bob. Bob, thinking that the request comes from Alice, will encrypt that challenge using the shared key that he knows, but of course Trudy doesn't know. So we'll encrypt um, that challenge, send the response back, and also a challenge to Alice. Of course, Trudy is the one who's going to receive that challenge, but Bob doesn't know that. And so for Trudy to authenticate herself to Bob, we'll have to send the encrypted version of the challenge R sub B using the key that only Alice and Bob know. And so the design of the protocol was such that it was believed that Trudy would not be able to do so because she does not know the key. And it turns out, even though she doesn't know the key, she can actually get this message somehow. So the idea is for Trudy to, after these 2 messages have been sent and received, is to do something really smart, which is to stop this protocol for a while and to initiate a different version of that same protocol with Bob. So, of course, this being processes, you can initiate as many communication sessions as you want, and you can just send any number of messages back and forth. So Trudy is now going to initiate another version of this protocol with Bob, and she's going to send to Bob the following request. She's going to again pretend to be Alice. And here I'm going to use the concatenation symbol just to be consistent with this notation here. Notice I didn't use concatenation here, but this is what I meant. And she's actually going to send R sub B to Bob. Notice R sub B is the challenge that Bob just sent her in that earlier exchange. So she's going to ask Bob to authenticate himself using this challenge, which is the one that he sent her to authenticate herself to him. So of course, Bob, following the protocol without worrying about anything, say, "Oh, Alice is trying to authenticate herself. She gave me also a challenge for me to authenticate myself. So I'm going to write back to her, and I'm going to do what the protocol tells me to do. And the protocol tells me to encrypt this challenge she sent me using the key that only I and Alice know." Okay. And he's also going to send her some other challenge because he thinks that Alice is trying to authenticate herself in another session. But what um, Trudy is going to do is she's going to ignore this part of the response. In fact, she's not going to respond to Bob at all. And so, in all of these protocols, there's always a timing mechanism. And if Bob doesn't get an answer within a particular interval of time, he's going to assume something went wrong. The connection was lost or something, and he's just going to abort. They're both going to abort this version or this execution of the protocol. But it's okay because it's too late. It's okay for Trudy because she already got this message from Bob. So now she can use it back in the previous session. So just to be clear, the order of things here is that step 1 and 2 happen first. Then Trudy takes a break from this protocol execution. She's going to initiate a new session, ask Bob to authenticate himself using this challenge that Bob sent her. Then she's going to get an answer from Bob. And now she can go back after aborting the second run of the protocol. She can go back here as sent to Bob whatever Bob just sent her. So that is the encrypted version of his challenge to her, encrypted with the key that she doesn't know. And this is the point. Bob receives this response and says, "Oh, the other person was able to encrypt my challenge using the shared key, so that person is definitely Trudy. Sorry, definitely Alice." And so Trudy successfully impersonated Alice to Bob. And of course, Bob also authenticated himself to Trudy, but that's not the problem. That's not the goal that Trudy was after. She was after the goal of impersonating Alice, which she did. So, how did this attack work? Well, the way the attack worked was that Trudy was able to trick Bob into encrypting his own challenge. The challenge R sub B that Bob sent to Trudy for Trudy or Alice to encrypt, he was tricked into encrypting it himself and therefore giving the answer to his own challenge to the attacker. And the attacker was able to send this response back to Bob. This is the response that Bob actually generated himself without knowing it. So, bottom line is this so-called secure mutual authentication protocol does not work because of this attack. And maybe you'll be able to find some other attack as well. And if you do, please let me know. That would be cool. So I think I want you to take away several points from this. The first one is that it's generally not guaranteed that a protocol that is secure for one-way authentication. And this protocol was secure, unless you can break it, and please let me know. This was a secure way for Alice to authenticate herself to Bob. But this one-way protocol was not secure when we used it in a two-way fashion to do mutual authentication. So the second related conclusion you should learn from this is that protocols are very subtle. Okay, so something that works in one direction, if you do it the logical way in two directions, exactly the same secure protocol becomes insecure when you do it in both directions, even though you use two different nonces, which is the right thing to do. And this is true even though, remember, the underlying crypto is assumed to be secure. Notice we assumed, and in this case, the algorithm that I use to generate the pseudo random numbers and the encryption algorithms are completely secure. They're cryptographically secure. We didn't break the crypto. But even though the building blocks were secure, the protocol itself was not secure. So remember, protocols can be very subtle. And I guess a third related conclusion is that simple changes to a protocol can have significantly drastic consequences. So again, we just took a protocol that actually worked, and then we just made a simple change to it. We just executed twice in a row, say, and that made it into an insecure protocol. So how are we going to solve? So this is a failed attempt. Can we actually come up with a third attempt that will successfully mutually authenticate users to each other? And here is a proposal. So the proposal is to prevent the previous attack is to make sure that every time one user authenticates themselves to the other user, they encrypt not just the challenge, but also a string that is specific to them, like their name or their identifier. So in this protocol, Alice sends her identifier and a challenge to Bob. Bob will take this challenge, it will concatenate to it, and that's the difference. It will concatenate to it a string that is personal or specific to himself, say his name, and he will encrypt that with the shared key. And of course, he's also going to send a challenge to Alice so that she can authenticate herself to him. And when Alice responds to this challenge, she will not only encrypt it, but she will also prepend, say, her own identifying string to the challenge before she encrypts it to send her response. So again, remember the third lesson we just drew earlier was that a subtle change to a protocol can have drastic consequences. And so here we claim that this very small change, just adding, say, their own identifying string to the nonce before you encrypt it, will make this protocol secure. So why is it the case that doing this small change right here will make the previous protocol, which was insecure, suddenly secure? So the reason is because now Trudy, the attacker, will not be able to trick Bob into giving her the response that Alice was supposed to send to this challenge, because if she did the same trick as in the previous slide, she would actually ask Bob to encrypt this challenge. But when Bob responds, it will not be encrypting this string. It will be encrypting the string of his own challenge preceded by his own name, not Alice's name. And so Trudy will not be able to capture this response and send it back as if it was coming from Alice, because it will not have the right identifier string in it. So I want you to pause the video and make sure you try to simulate what would happen in the case where Trudy would try to execute the attack on the previous slide. And with this mechanism, you would see that it would not work because of this identifying string. So again, the lesson here is that a very small change to a protocol like here can have a drastic impact on its security. In this case, we went from a completely insecure protocol to a much more secure protocol just by the insertion of an identifying string, a concatenation step prior to the encryption step. And another lesson that maybe we can try to generalize from this example is that it's typically a bad idea to take a protocol like we did in the previous slide and just have it performed identically by the two sides of a communication scenario. So it was a bad idea to take a protocol that worked in one direction and then use it twice in both directions. We had to modify the two directions even a little bit, even in a subtle way, to make it secure. So typically, I mean, there's no general rule here, there's no theorem, but an intuitive or a rule of thumb is that if you have a protocol that works in one direction, it's typically a bad idea to use it unchanged in two directions and hope that it will remain secure.